Okay, so we're going to continue finding zeros of a polynomial, and we're going to continue talking about the rational zeros test, but I have two tricks that will help you eliminate your possible zeros, okay? That problem that we did from our homework, there was like 12 or 14 zeros that we could try, right? That even though that's a small amount compared to an infinite number, it's still quite a few zeros, right? So I'm going to give you a couple ways that we can eliminate some, okay? First of all, we're going to talk about Descartes' rule of signs, okay? So Descartes' rule of signs, this is just a polynomial, okay? We have a polynomial. This is what it says. If so we're looking at positive zeros and negative zeros with Descartes' rule of signs. So the number of positive real zeros of our polynomial is equal to the number of sign variations of f of x, or less than that by an even integer. I'm going to let you write that down, and then we're going to dissect what that means. So if we look at f of x and we look at the number of variations in sign, that means adding versus subtracting. So x squared plus 2x minus 1. There is one change in sign. We go positive, positive, negative. That would be one change in sign, okay? So that's what that means, variation in sign, looking at adding versus subtracting, positive versus negative through your polynomial. So as you look in order of your polynomial, the number of sign changes, that's how many positive real zeros you have, or an even integer less. Okay, why an even integer less? Okay, let's talk about complex zeros. What's true about imaginary zeros? They come in pairs, okay? So we have to account for that. So if we have 3 sign changes in our polynomial, that means we could have 3 positive real zeros or 1 positive real zero, because there could be that possibility of 2 imaginary zeros. Okay? If we have 4 sign changes in our polynomial, then we could have 4 positive real zeros, or we could have 2 positive real zeros, because there could be 2 imaginary, or there is a possibility of 0, because they all could be imaginary. Okay, so you're basically going to count the number of sign changes and then keep subtracting 2, because there could be 2 imaginary zeros. Okay, so if your number is 3, then you're going to say 3 or 1. Okay, your number is 5, 5, or 3, or 1. Okay, because we don't know about those imaginary zeros, but we know they come in pairs. Okay, now this is for positive real zeros. If we look at f of negative x and count the sign changes, that will tell us how many negative real zeros we're going to have in our polynomial. So if we look at f of negative x and count the number of sign changes, that's how many negative real zeros we're going to have. Or less than that by an even integer. So the same rule applies here. Okay, we still have that possibility of these imaginary zeros. So if we count 3 sign changes in f of negative x, then we could have 3 or 1 negative real zero. Now, right now, it doesn't sound all that helpful, but it really is, okay? So we're going to do an example, and we're going to see how this can actually help us narrow down what zeros we should try, okay? Or what possible zeros we should try. Are you ready? Here we go. Write this down. F of x is 3x cubed minus 5x squared plus 6x minus 4. Okay, so using Descartes' rule of signs, how many sign changes do we have in our polynomial? This is positive, right? This is negative. This is negative. So 1, 2, 3. We have 3 sign changes. So that means we're going to have 3 or 1 positive real zeros. We have to account for the possibility of those imaginary zeros. So there are 3 sign changes, so there's 3 or 1 positive real zeros. Now let's look at f of negative x. Okay, what happens when we plug negative x in and we cube it? And it makes it negative. What happens when we plug negative x in and square it? It stays the same. And then 6 times negative x. Okay. How many sign changes are in f of negative x? There are none. Right? The signs never change. So what does that mean about our zeros? There are 0 negative real zeros. So what have we just done before we've even started picking zeros? We just got rid of half of our list. We're not going to try any of our negative real or our negative zeros. Okay. Let's write our possible zeros using the rational zeros test. We have factors of our constants, 1, 2, and 4, over factors of our leading coefficient, 1 and 3. So our rational zeros test, we would write plus or minus 1, plus or minus 1/3, plus or minus 2, plus or minus 2/3, plus or minus 4, and plus or minus 4/3. Right? So that's 12 possible zeros. We've just eliminated 6 of them. Okay, that's nice, right? Okay, let's go ahead and find these zeros. We did all this work. Let's apply it. So we had 3x cubed minus 5x squared plus 6x minus 4. What would you like to try first? 1. Okay. So we have 3. Gives us negative 2. This gives us 4. Man, you guys are on a roll. All right. We found one positive real zero, didn't we? So now, we're either going to get two more out of this, or they're going to be two imaginary. Let's look at it. So we know one is a zero, right? Left over, we have 3x squared minus 2x plus 4. Can we factor that? No? Sean says we cannot factor it. Okay, we can complete the square, or we could do, what's our other option? Thank you, the quadratic formula. Let's do that just to remember it. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. All right, so we have 2 plus or minus the square root of what? This is 4 minus what? This is 4 minus 48, so negative 44. How do you reduce something like that? How do you reduce the square root of negative 44? Okay, so an I comes out, and we know the square root of 4 is 2. So 2 radical 11 times I. Right? So we found 2 imaginary zeros. Okay? So our zeros we found are 1 and then 2/3 plus or minus 2 radical 11/3 I. I will tell you on your homework, I think your zeros will be a little bit nicer than that, but it is possible that you will have to use a quadratic formula if you cannot factor. If you'd rather complete the square, go for it, but I wanted to do at least one example of the quadratic formula in class. You have a question?
Yeah, isn't 6 at the bottom of the
Huh. Thank you. 6, 6, so this would go to 1/3, right?
Yeah, isn't what you needed?
Well, it's negative b, and since this is negative, it's a positive 2.
Oh, okay.
Okay. Now, we're going to talk about another trick. Descartes' rule of signs you will be evaluated on. I will ask you a question on the test about Descartes' rule of signs. And it's really helpful, and I want you to use it from here on out. Now, I'm going to show you what I call an upper bound and a lower bound. This is not something you have to use, but if you understand it, you can use it. Okay? Descartes' rule of signs is where I want your focus. Okay? If you want to use the upper and lower bound, please feel free. Okay? So, our upper bound rule is that if we take a polynomial with a positive leading coefficient and we divide it by x minus c using synthetic division. Okay, so I'll let you kind of write that down. This is bothering me. What? This spacing. There we go. So if we take our polynomial and we use synthetic division with x minus c, then if c is positive, And our last row, when we do synthetic division, if they're all positive or zero, then C is an upper bound, which means don't try any zeros above that. So if you do synthetic division with a positive zero, and your last row is all positive or zeros, then it's an upper bound. Don't try any zeros above that number. Right. So if you plugged in 1 and it met this description, then don't plug in your 2 and 3 that you have written down, because they're not going to work either. And then we have a lower bound if we use a negative possible zero, and our last row alternates between positive and negative. In a zero, we can count either way. So if they alternate signs with a negative possible zero, then we have a lower bound. Don't try anything lower. Okay, so I have an example, and I have zeros picked specifically so that I can show you how this works. Okay, do people still writing? Are you ready? Amazing. Okay, so here's our polynomial. Let's create our list of possible zeros. Factors of our constant. One and two. Factors of our leading coefficient. So we have 1 and 2. We have 1/2, and 2 over 2 is 1 again, so we don't need to write it. We have 1/3 and 2/3. We have 1/6, and 2 over 6 is the same as 1/3, as we already have right now. Okay. Now, you're probably not going to do this on your paper, but I'm going to write all of these out in order so we can visually see what's happening. Okay, so our smallest number is -2, and then -1, -2/3, -1/2, -1/3, -1/6, 1/6, 1/3. And you don't have to do this, I'm just doing this for effect here. Did I get them all? Okay. So, regardless, what's the first number we always like to start with? 1. So I'm going to set up my synthetic division here. 1 is a positive possible zero, correct? Okay. So when we do the synthetic division, we get 1, 1, why, yeah, I don't know. 1, okay, so we drop down to 6 times 1 is 6, thank you. 2, 2, 5, 5, and 3. Alright, so first of all, we didn't find a zero. That is sad. However, we plugged in 1, It was a positive possible 0. This last row is all positive numbers, so that means it is an upper bound. Okay, so this is an upper bound. Which means 1 isn't a 0, but then 2 isn't going to be either, so don't try it. Okay. Which is something you would want to plug in to avoid those fractions, right? But don't, because it's not going to work. Okay. Okay. Now, let's try this again. And I'm going to pick negative 1/3. Okay, this will be good practice for us. Drop down the 6. 6 times negative 1/3 is? Okay, so this adds to negative 6. Negative 6 times negative 1/3 would be positive 2. And we have 5 times negative 1/3, which would be negative 5/3. Okay, now we know that this is not going to have a remainder of 0. And we don't really need to know the remainder, but what sign value is it going to be? It's going to be negative, right? Now, we have a negative C value, and we alternate signs, which means negative 1/3 is a lower bound. It was a negative C value, and our signs alternate, so we have a lower bound. So negative 1/3 was not a 0, but these aren't going to be either. Don't try that. We are going to do one last example of finding the zeros, and then we'll talk about our quiz. Okay. So here we need to write this as a product of linear factors. So in order to write the factors, we need to find the zeros. Well, the zeros can help us, right? If we can't factor it, which this is a 4th degree polynomial, we want to find some zeros to help us, right? So first of all, how many positive real zeros are we going to have using Descartes' rule of signs? We have how many sign changes? Positive to negative, negative to positive, positive to negative, negative to positive. So we could have 4, or 2, or 0, positive zeros. If we look at f of negative x, how many sign changes are in f of negative x? None. Should we try any negative zeros? No. So, rational zeros test. Let's list our possible zeros. Factors of the constant term would be 1, 2, and 4. Factors of our leading coefficients. Okay, so I'm going to leave it like this. We only have 3 zeros to try, don't we? Because we're not going to try the negative ones. So, we have 1, negative 2, 5, negative 8, 4. What do you want to try? 1. So drop down the 1, multiply, add, multiply, add, multiply, add. Look at that, guys. We found a 0. Okay, now we're trying to factor this, correct? That's our goal, is factoring, not zeros. So let's remind ourselves that this means x minus 1 times x cubed minus x squared plus 4x minus 4. Okay? Can we use synthetic division again? Do we have to? We can factor by grouping, and if you recognize that, that is going to be faster than doing synthetic division again. So let's go ahead and factor this by grouping. GCF of the first two. Left over is x minus 1. GCF of the second two. Left over is x minus 1. Okay? So this factors to x minus 1 times x squared plus 4. And don't forget, we still have this x minus 1 from the 0 we found before. Now, if we want this as the product of linear factors, what are we going to have to do with this? This is not linear. What are we going to have to do with that? We're going to have to find those zeros. So if we set this equal to 0, that means x squared is negative 4, correct? Which means x is what? Careful. Plus or minus 2i. Remember, it always comes in pairs. All right. So, our linear factors would be x minus 1 times x minus 1, x minus 2i, and x plus 2i. Okay. If you have the zeros, you can write the factors. Okay. So at this point, I have given you lots of tools to help you. Please choose the route that is going to be the quickest. Okay. If you can factor by grouping, that's going to be quicker than plugging in zeros for the rational zeros test. Use Descartes' rule of signs to eliminate zeros. Use the upper and lower bounds if you find that they are helpful. Okay. So here is your homework. Not very many problems once again. On number 82, it does say something about use your calculator. Don't do that. I don't want you to do that.